Flexural behavior of reinforced concrete sections. Let us first discuss what are the different types of structural members. We have four important types of structural members: beams, columns, slabs and footings. Beams are generally horizontal structural elements. These are capable of withstanding vertical loads. They transfer loads from slabs to columns. Loads are transferred by beams in the form of shear forces and bending moments. Now coming to columns. Columns are vertical structural members which carry load by compression. They are effective in transfer of loads from the roof slabs or beams to the foundation. Now coming to slabs. Slabs are constructed to create a flat and useful surface such as floor or roofs and ceilings. Slabs are generally plate-like structures. They are supported by beams, columns or walls. So any load which comes over a slab will get transferred to the nearest beams and then to the columns and finally to the foundations. And slabs are typically larger in dimension along the length as well as its width. And generally the thickness of slab is very small compared to its length as well as the width. And finally, footings. Footings are very important structural elements which maintains the stability of the structure on the soil or ground. They are capable of transmitting loads from the entire superstructure to the underlying soil below the structure. Now coming to the flexural behavior. Among the structural members we have discussed, only beams and slabs are flexural members. What do you mean by flexural members? Or what do you mean by flexure? By flexure or bending, we mean the structural members when subjected to loads acting in the direction transverse or perpendicular to its axis, the structural member undergoes bending. The bending is otherwise known as flexure. You see this structural member, the figure here shows a typical concrete beam. The beam has an axis like this, and when you subject it to loads in the perpendicular direction, the beam bends. And what happens to the beam? The beam, when it bends, the beam fibers above the neutral axis tend to come closer to each other and they experience compressive stress. And what about the fibers below the neutral axis? They tend to move away from each other and they experience tensile stress. So the same structural member develops both tensile stress as well as compressive stress in the cross section on either side of the neutral axis. So that is the speciality of a flexural member. It develops both tensile stress as well as compressive stress in the cross section on either sides of the neutral axis. But you know that concrete is very weak in tension and strong in compression. Since concrete is weak in tension, it is incapable to take the tensile stresses developed in such flexural members. Hence we embed steel bars in the tension zone of the concrete. Okay. We have already studied about the design stress strain behavior of concrete as well as steel. Concrete, as we know, it is weak in tension. So we completely neglect the effect of concrete on the tension side of the flexural member. So we are interested only in the flexural compression. This we have already discussed. The design stress strain curve of concrete shows a parabolic initial region up to a strain value of 0.002. Up to a strain value of 0.002, the curve is parabolic in nature, and the corresponding design strength in concrete is 0.45 FCK, and this stress value continues till the ultimate strain of 0.0035. So when the concrete reaches a strain of 0.0035, concrete fails. What is the maximum strength or the design strength of concrete? 0.45 FCK. So these values you should be thorough with. You should remember that the design strength of concrete is 0.45 FCK, and the initial portion of the curve is a parabolic curve, and it continues to be parabolic up to a strain value of 0.002, and after which the strength value remains constant up to the final compressive strain of 0.0035. Now similarly, we discussed the design strength of steel. Shown here is a typical design curve of HYSD bars. As you increase the load, the stress strain behavior is linear initially, followed which it becomes non-linear and reaches the yield point. What is the design yield strength of steel? It is 0.87 Fy. It is also very important value. What is the strain at which the steel yields? The yield strain is given by 0.87 Fy by Es plus 0.002. After this value of yield strain, the steel undergoes large deformation without increase in stress. So this typically shows its ductile nature. It can stretch a lot without increase in stress. Now we are most interested to know how the reinforced concrete beam undergoes deformation across any particular section, for which we invoke what is known as the Euler Bernoulli assumption. According to Euler Bernoulli assumption, plane cross sections of any beam remains plane even after the beam bends. Shown here is a small beam element. A part of a beam is shown here in solid line, and when it is subjected to loads, it undergoes bending. The bent profile is also shown here using dashed line. You can see. Now you observe the cross sections. The sections here was initially plane section, and it remains plane even after bending. So that is the assumption of Euler and Bernoulli. And what is the consequence of this assumption? Why do we make such an assumption? According to this assumption, only if the cross sections remain plane, we can come to the conclusion that if this represents the neutral axis of the beam, the deformation on either sides of the neutral axis increases linearly as you go away from the neutral axis. As you move away from the neutral axis, the deformation also increases. As you come closer to the neutral axis, the deformation is also decreasing. So that is exactly what is shown with the help of this strain distribution diagram. As you move away from the neutral axis, more is the fiber getting compressed on the upward side of the beam. At the bottom side of the beam, as you move away from the neutral axis, the more it gets stretched. So the extreme fibers are subjected to maximum strain or maximum deformation, which is explained with the help of the strain distribution diagram. And you should bear in mind that this strain is always a straight line. So that is how we make this assumption. The assumption results in straight line distribution of strain. Now even if you increase the load, you keep increasing the load, the strain at the extreme fibers keep increasing, but the distribution remains a straight line like this. The strain keeps increasing. All the fibers above and below the neutral axis, they get strained more and more if you keep increasing the load, but the distribution remains the same. It is straight line. Okay. Coming to classic flexure formula, we are invoking this formula to understand the stress distribution in a reinforced concrete structure, for which we know the theory of bending. We have already learned it in our lower semesters. According to this, m by I is equal to sigma by y is equal to E by R. You see, this beam, when subjected to loads, it develops bending moment at every section, and you can find the bending moment at a particular section and you can use it here. So that is the bending moment m divided by I. What is I? The moment of inertia of that section. If it is a rectangular section like what is shown here, you can definitely find the moment of inertia of that section. Now coming to sigma. What is sigma? Sigma is the bending stress at any particular fiber in that particular cross section. You have this cross section and you want to find the bending stress at a particular fiber level, and that fiber may be located at a distance y away from the neutral axis, and using this equation m by I is equal to sigma by y, you can easily find it out. And what this equation gives is that sigma is proportional to y, because m is constant and I is constant at any particular section. Sigma can be said to be proportional to y, which when you substitute y is equal to 0 here, you can get sigma is equal to 0, which means at neutral axis there is no stress. So that is what is shown here in this stress distribution diagram. As you move away from the neutral axis, stress is also increasing linearly, so you definitely get a straight line stress distribution here. But one thing we should bear in mind is that the stress distribution diagram is a straight line only when the stress in that material is well within the elastic limit. So the material should ensure Hooke's law, or the material should satisfy the linearly elastic region in order to say that the stress distribution diagram is a straight line. The stress distribution diagram can be a straight line only when the material is loaded well within the elastic limit. But in case of strain distribution, we said whatever be the loading condition, strain distribution becomes straight line always. It is always a straight line. But in case of stress distribution, it is not so. Stress distribution diagram is a straight line only in such condition the stress is within the elastic limit. Now from this figure it is very clear that the stress is maximum at the extreme fibers, at the compression side as well as on the tension side. Concrete at the extreme tension fiber is experiencing very large stress. As a result, when you increase load at a stage of loading, the concrete undergoes cracks. The concrete is no longer able to withstand the tensile stress, and when the stress exceeds when it exceeds the tensile strength of concrete, immediately it cracks. But compression side remains intact because concrete is very safe in compression. Such a tensile stress is known as the modulus of rupture. So modulus of rupture is explained as the maximum flexural tensile stress reached in the extreme tension fiber of a beam at which the concrete cracks for the first time. And that particular bending moment at which the concrete cracks for the first time is known as the moment at first crack, or the cracking moment, which is given with the help of this formula. Can be used to determine the cracking moment. M is equal to FCR into I by Y, where FCR is the modulus of rupture. Now coming to the case of reinforced concrete section when subjected to gradually increasing load. When you subject it to gradually increasing load, how the reinforced concrete beam behaves. You see, to explain this, we are using a moment curvature relationship. The moment curvature relationship is what is shown here, moment on the y-axis and curvature on the x-axis. Moment is indicative of the external load and the stress which develops in the beam, and curvature actually shows the response of the beam to such external loads. So as you increase the external load, the moment also increases, the bending moment in the beam section increases proportionally with curvature. And at this stage there is no cracks developed in the concrete beam. You see this section, the entire section is effective in resisting the bending moment, and no cracks develop in such a section, and we call it uncracked phase. it is known as uncracked phase. Here the strain distribution is a straight line, so is the stress distribution, which is also a straight line. And you keep increasing the load again and again, further you increase the load, and finally you say that at a particular bending moment in the section where the bending moment becomes equal to the cracking moment, the moment at first crack, the first crack in the section occurs, and then the concrete on the tension side becomes completely ineffective in resisting tension, and the same role will be carried out by the reinforced beam in the section. The steel bars in the tension side will carry the bending moment instead of concrete. The concrete becomes completely ineffective, and you see we have plotted the strain distribution only up till the level of steel, not beyond that, because it is concrete, which is about which we are not interested on the tension side. And stress distribution, you see the stress distribution is again linear because the load is still within the linearly elastic region, and we are not plotting towards the tension side of the concrete. As we already discussed, we are not interested in the concrete on the tension side because it is rendered completely ineffective. You keep increasing the load is still within the linearly elastic region, and this region we call it the working load region or the service load region, which is the loading condition which the beam generally experiences in its entire course of life. And during this phase, multiple cracks can occur in the tension side of the concrete section, and we call it linearly elastic cracked phase. And this is true up to a particular value of moment. We call it M service. Let us say it is M service. You can further increase the load, and now the concrete loses its linearity, the behavior loses its linearity, and now it tends to be non-linear. And at a particular point of load, the steel begins to yield. So as the steel yields, you can see multiple cracks occur because the steel is yielding very much, and there is huge increase in strain without much increase in stress. You see beyond this point there is large increase in curvature without much increase in stress, but without much increase in the moment. The moment carrying capacity of the section has reached its maximum and is not increasing anymore. So more cracks occur on the tension side, and you see the strain has increased very much on the tension side as well as the extreme compression side. Both the strain has gone up, but the strain distribution is still linear. And finally it reaches a point where the concrete crushes. The steel is yielding very much, the concrete on the compression side fails abruptly, and the beam fails. And here you see the stress distribution. The stress distribution of concrete has turned from straight line to a parabolic variation. This is typical of the non-linear cracked phase. So we call this phase as non-linear cracked phase. So let us summarize this graph again. We have three phases of or three stages of loading in a reinforced concrete beam. Initially it is the uncracked phase. In the uncracked phase, the applied moment is very small, less than the cracking moment. The stress developed is less than the modulus of rupture, and the entire section was effective in resisting the moment. But as we increase the load, the first cracks develop, and we are increasing the load further. The moment at the section exceeds moment at first crack, and the tensile stress also exceeds the modulus of rupture. But the loading is well within the elastic region, so we see a straight line there. The concrete on the tension side becomes completely ineffective in resisting the moment. It is the steel which is effective in resisting the moment on the tension side. So we call such a region as the linearly elastic cracked phase. And we keep increasing the stress. The moment exceeds the cracking moment very much, and it has gone much larger than the cracking moment. As a result, the large cracks develop, and later we have seen the steel is yielding. A large curvature occurs in the beam. As a result, more and more cracks develop on the tension side, and finally, whatever be the case, the reinforced concrete beam fails by crushing of concrete. So crushing of concrete is the limiting state of collapse of any flexural member. So we call such a phase as the limit state of collapse in flexure. So we are interested to analyze this particular phase for our design of RC members. And one thing we must bear in mind, that there is a possibility that steel can yield and it may not yield also before the final crushing of the concrete, about which we shall study in the coming slides.